In this example, we want to take the rotation matrix given by cosine theta, negative sine theta, cosine theta, and prove that it's an orthogonal matrix. Now, orthogonal matrices are important because they represent rigid transformations. So they preserve lengths and angles. The telltale sign that a matrix is orthogonal is that the inverse is equal to the transpose. So a matrix M is orthogonal if and only if M inverse is equal to M transpose. Okay, well, if M is cosine Z, negative sine Z, sine Z, cosine Z, M inverse is equal to 1 over to the determinant. That's going to be cosine squared Z plus, minus, I should say, negative sine squared Z. Double negatives here cancel out. And we swap the cosine z's. And we make the off-diagonal elements the negative what they started with. So as we said just a second ago, this double negative becomes a plus and a plus. Cosine squared z plus sine squared z is equal to 1. So this is equal to 1 times cosine z, sine z, negative sine z, cosine z. And so what do you know? This is equal to M transpose indeed. Okay. So again, why is this important? What this tells us is that when we take this matrix and multiply it by a vector, the rotation matrix is going to rotate the vector, but not change the length of the vector. Because one important property of an orthogonal matrix is that M times a vector x, the length there is equal simply to the length of x. Okay, so when we multiply this rotation matrix by a vector, the length of the vector remains unchanged.